Session 2024, here we talk about atom and photoelectric effect. So we'll start. The aim of this exercise is to study some lines of the emission spectrum of the mercury atom and use one emitted radiation to produce photoelectric effect. So the document 8 shows a simplified energy level diagram of the mercury atom. We have document 9, which shows some lines of the emission spectrum of the mercury vapor lamp and air. And you have all these givens. So the question is, the mercury atom considered in the third excited state n equals to 4 absorbs a photon with energy E. It then passes to the fifth excited state n equal to 6. So we continue now. Calculate, the question is calculate E. So when we say here calculate E, إذا بنلاحظ E is the energy of the photon. So أول شيء we have to pay attention أنا شو عم بشتغل absorption. So if I'm talking about absorption, this means that, so I'll write here the solution. This is 1.1. So since I'm talking about absorption, this means I'm talking about excitation of the atom. Excitation, this means the atom was in an initial state, then it absorbs gain photon energy by the photon, and then it reached the final state. Now, هون عم بيقلنا it was in a third excited state, which is E4. So then this is E4 plus E of the photon, عطينا إياه, he called it E, and it will now be in the fifth excited state, and this is E6. So the question is to find E of the photon, then E is equals to E6 minus E4, then which is equals to, we have E6, it's equals to minus 2.69, okay, so that's it. So minus 1.58, and minus E4, which is minus 3.73. So the answer will be equals to 2.15 electron volt. Then this is the energy of the photon that will be absorbed in order for the atom to pass from the third excited state into the fifth excited state. Now, part 1, 2. Calculate the wavelength of this photon. So we have E of the photon is equal to hc over lambda, which means that lambda equals to hc over this E of the photon is given E. but هون بدنا ننتبه لشيء انه انا هون ال E ما في خليها بالالكترون فولت، لازم تكون in SI unit, which means in joules. So we put all the values. This is H is given as 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8 and all over E. هلا بنلاحظ انه E طلعت معنا 2.15 بس electron volt. So انا لازم احولها هون. So times 1.6 times 10 power negative 19, and then we get lambda حيطلع عنا 5.78 times 10 to the power negative 7 meter. Part 1.3. Deduce, but without calculation, the value of lambda when it passes from 6 to 4. So أول شيء هلا أنا بلاحظ إنه عم بيعمل D excitation. من 6 عم ينزل عند 4. In air associated with the transition 6 to 4 represented in the document 8. هلا لنقدر نعرف اللامدا corresponding. أول شيء I will say that we're doing a D excitation. D excitation from E6 to E4. طيب إذا دي excitation يعني حيعطيني لامدا. So بيجي بطلع على diagram here عم يعمل دي excitation so حيعطيني a certain لامدا. طيب ما هيدي اللامدا هي ذاتها the wavelength needed for the atom to be excited from the 4 to the 6. It's the same lambda. So لكن in this case, and we already found it, so لكن طلع معنا lambda is how much? It's 5.78 times 10 power negative 7 meter. This is the wavelength of the photon needed for the atom to pass from the 4 to the 6. واللي هي ذاتها the lambda needed due to the de-excitation from the 6 to 4. So like in here, we will just say lambda from 6 to 4 is equal to the wavelength okay, is equal to the wavelength of the photon, okay, when it's pass or directly for the atom to pass from which level to be excited from 4 to 6, which we have it. So like n equals to 5.78 times 10 to the power negative 7 meter. Part 1.4, indicate using now document 9 the color of this emitted radiation. So I the color of this emitted radiation in this case. Just 1 minute. So we go here to the diagram. This is the diagram document of document 9. And then بدي اجي اطلع على الفاليوز اللي احنا اللي بيطلعوا لنا. هلا بنتبه هون انه اللامدا معايا بالنانومتر. So اول شيء بدي لاحظ انه I have to put this in nanometer. Now هيدي let's say in nanometer, then it will be 578 nanometer. Yeah, times 10 to the power 9. Then in this case, I look at the diagram and I know that the 5, 7 is here. So like, and this is the yellow color. So from the document, this radiation corresponds to the yellow color. Okay, now we continue the question. A filter placed in front of the mercury vapor lamp allows the radiation of blue color to pass. So بيقدر يخلي البلو color يمرق. Show that the radiation of the wavelength lambda, when this de-excited from 5 to 2, associated to this transition, passes through this filter. لأعرف إنه it passes through the filter، أول شيء I have to find the wavelength. And then بدي اطلع هيدي الويف length. إذا كانت هيدي الويف length correspond to the blue color, then in this case, yes, في يقول إنه okay, the filter, it will pass through the filter. So again, first of all, I have to find lambda of this transition. So here, part 2, I'm doing a de-excitation. I'm تعمل 5 let 2, so it's de-excitation. Then in this case, it was initially at level. It loses a photon, this is minus, and then it reached the final level. The initial level was the 5, then it loses a photon, and it reached the level 2, E2. Now, this means that the energy of the photon is equals to E5 minus E2, which is in this case, if I look at the values, so this is E5, and this is E2. So we have the values from the diagram. Then we put the values and we'll obtain 2.86 electron volt. But the question is to find if it passed through the filter. So بقى بطلع اللامدا لأعرف إذا هي blue color. طيب this is E of the photon. So we'll say E of the photon equal HC over lambda, which means this lambda equal HC over E of the photon. كمان مرة we have to pay attention إنه اليونت اللي احنا طلعناها it was in electron volt. So times 10 to the power 8. E of the photon is 2.86. كمان I have 1.6 times 10 to the power negative 19. Let's see in joules. And then we get the answer 4 times 10 to the power negative 7, 4.34. Which is if I have to put it in nanometer, so it's 434 nanometer. Now بيجي بتطلع على هيدا الرقم 4.434 nanometer, it's here. So yes, it corresponds to the blue color. So here implies it corresponds to the blue color, which means yes, it can be in this case. So the question, does it pass through the filter? So yes, it passes through the filter. Now, part 3, this lamp equipped with this filter illuminates separately two metallic plates. So هيدي اللمبة اوكي عم بتضوي two metallic plates, one made of cesium and another made of zinc, such that we have the work function of the cesium at this much and the work function of the zinc at this much. 3.1 define the threshold wavelength of pure metal. So بنعرف إنه threshold wavelength هي عبارة عن the maximum wavelength needed for the radiation to be capable of what? Of extracting an electron of the metal from the surface of the metal. So لكن هون if we have to put the definition, it is the maximum. بينما لو سألنا عن الانرجي كنا هنقول بالنسبة للانرجي it's the minimum energy needed. Okay, so they are inversely proportional. يعني بالنسبة if we want to talk about the work function. So لكن here it's the maximum wavelength of the radiation capable, which is capable of extracting an electron from the metal. أكيد from the surface of the metal. Okay. Now, calculate the threshold wavelength of each of these two metals. So we have كنعطينا W0, the work function of the cesium was 1.89 equal 1.89 electron volt. So we have to find the threshold wavelength, which means Hc over lambda 0 equal 1.89. We have to pay attention. It's equals 1.89 بدي times 1.6 times 10 for negative 19, let's say in joules, which means that lambda 0 equals Hc 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8. This is H times C over all this value. So if we do the calculation, then in this case we'll get as answer 6.57 times 10 to the power negative 7 meter. إذا بدي أحطها in nanometer, then it's 657 nanometer. As for the second one, for the zinc, so كمان نفس الشيء, we'll say lambda 0 equal Hc over W0. But the W0 here اللي عطينا إياها for the zinc, so W0 equal 4.31. Then in this case, times 3 times 10 to the power 8 all over 4.31 times 1.6 times 10 to the power negative 19. So we get as answer 2.88. كمان إذا بدنا نحطها in nanometer, so we multiply by 10 to the power 9, then we get as answer 288 nanometer. The last question, part 3.3, the photoelectric effect takes place in one metal. Deduce which one. نحن ليصير في عندي photoelectric effect عادة we can compare the energy. So بنقول إذا ال energy of the photon is bigger than W0, so we say usually if the energy of the photon is bigger than W0, so we have photoelectric effect. Photoelectric effect, and we have then this means we have emission of a certain electron, extraction of electron. طيب هون I can compare also lambda, بس كيف بدي أعمل compare lambda? الانرجي واللambda are inversely proportional. So for the photoelectric effect to happen, we must have lambda is smaller than lambda 0. طيب let's see now. In our case نحن كنا مطلعين اللامدا تبع light, okay? And طلع معنا اللامدا تبع light is equals to 4. Just let us see. Okay, so let's see here. This is the cesium. So this is for the cesium. Just let us put this for the cesium here. And this is for the zinc. Okay. So in order for the photoelectric effect to happen, we need lambda to be smaller than lambda 0. Okay. So إذا بنجي نطلع على الأرقام اللي نحن ديجا كان معنا إياه هون. here the value, so we notice that lambda اللي طلعت معنا, which is for the filter, is 434 nanometer. So the 434 nanometer here is smaller than the 657 nanometer, which corresponds to who? To the cesium. This means that the photoelectric effect will happen for the cesium or with the cesium.